Hello everyone and welcome. Today we're going to be talking about the periodic table and periodic law, and we're also going to be talking about periodic trends. Okay, so this is two lessons essentially in one. It has to deal with sections 1.5 and 1.7 from our textbook. So let's go ahead and let's get right on in. Okay, so the first thing that we're going to be looking at, okay, let's not worry about this. We'll talk about this after. Well, actually, you can read it. We'll be talking it throughout the lesson. But the first thing we're going to talk about is we're going to talk about drawing Lewis structures. So we looked at drawing Bohr-Rutherford diagrams, but as you guys all are aware by now, is that after element number 20, it breaks down. Okay, so once again, if you think about your octet rule, okay, we have our first energy level, which is these first two. Then we have our second energy level, our third, and then our fourth. And once we hit our fourth one, then we have way more than 8 electrons in that valence shell, so things break apart. Okay, now, just to kind of recap, chlorine and lithium are already done for us. So what I'll do is just on the back here. Okay, so let's say we're drawing chlorine. Okay, so for our Bohr-Rutherford diagram, okay, we're gonna have our protons and neutrons in the middle. So our protons for chlorine is 17 because it's atomic number 17, and it has a mass of about 35. So 17 plus 18 should give us 35 there. So we have our first shell. And in our first shell, we have 1 and 2. Okay, in our second shell, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 10. And then in our third shell, we're going to have 1, 2, 3, 4, 5, 6, 7, and that gives us a mass or a grand total of 17. Now, do we need to draw this every single time that we're looking at elements? No. What we really care about is the valence shell. Protons, neutrons, we can figure that out. We don't need to have to draw it. Okay? What we really care about is the valence shell. So this valence shell has 7 electrons. And the reason why it's important to us, because it's going to tell us that chlorine is going to make a 1 negative charge and who it can bond with and so forth. So we really care about our valence shell. So instead of drawing Bohr-Rutherford diagrams, we're going to draw Lewis structures. Now, Lewis structures are extremely simple to draw. You only need to know 2 things. The first thing is, what is the atomic symbol for chlorine? Well, the atomic symbol is Cl. And once again, you could just look at your periodic table to figure that out. The next thing you need to figure out is, how many electrons does it have in its valence shell? So chlorine has 7, and we already did that by drawing our Bohr-Rutherford diagram. So all we need to do is we just need to draw the dots. 1, 2, 3, 4, 5, 6, 7. And that's a Lewis structure for chlorine. Much simpler, much quicker, and we could do the exact same amount of work as if we did a Bohr-Rutherford diagram. Okay, so let's try one other one. Okay, we could try oxygen. Okay, so once again, if you like to pause the video to try and draw it out, you can. And then when you're ready, just come back and see if you got it right. So oxygen. So once again, we only need 2 things. We need to know the symbol. So oxygen is nice and easy. It's an O. And how many valence electrons does it have? Well, it has 6. So I'm going to draw 1, 2, 3, 4. Remember, you have to always go around once first before you can start doubling up. And then the second one, we would have 1 and 2. So that's oxygen there. Now, where people struggle with is trying to figure out how many valence electrons we have. Okay? So, this is how you figure it out, the simplest way that I can show you. Okay? Group 1, your alkali metals. These all have 1 valence electron. So hydrogen Once again, if I have to draw hydrogen, I draw H, and it has 1. Same thing with lithium, 1. Okay, so all of these ones in the first group have 1 electron. Everything in the second group has 2 electrons. We're going to skip the transition metals, and then we go to group 3. All of these ones have 3. All of these ones have 4, 5, 6, 7, 8. Okay, that's what we're going to be dealing with in grade 11 chemistry here. Now, what about the transition metals? Well, 2 things that you need to remember. The first one, whatever number is bolded, that is the one that you're going to use when it's not specified. Okay, so for example, let's look at copper. Copper, you can make 2 charges. You can make copper 2 or you can make copper 1 because there's a 2 and a 1 there and they're both positives. Positives means that they're going to lose electrons. Okay, negative means you gain. So for copper 2, okay, so we'd have copper 2 and we could have copper 1. So copper 2 has 2 there. Copper 1 has 1. So as you can see, they're both different. Now, if I just said to draw copper, well, which one would you do? Well, you'd have to look at and see which one's bolded. Well, copper 2 is bolded here. So this would be the more abundant. Once again, we looked at that last lesson with your isotopes and stuff like that. This would be the one that is more abundant. Even though these aren't isotopes, they're similar idea, multivalent metals they are. But this is the one that's more abundant, the more common, the more stable one. So that's the one that we would pick. Okay, and same thing with any other one, right? There's lead. You can have lead 2 or 4. Lead 2 is bolded, so that's the one that we would use. All right, so once again, you need to just make sure that you know how to come up with those there. All right, so a couple other things that we're going to talk about. Okay, our subatomic particles. So by now you should know we have 3 of them. We have electron, proton, neutron. Okay, we denote them as E negative because an electron is negative, proton positive, neutron neutral or a 0 charge. Okay. Now, what are their actual charges in coulombs? If you've taken physics before, you may have seen this. Okay, a coulomb is the higher the number, the more of a charge it has. The lower the number, the less of a charge. So an electron and a proton have equal charges. Okay, one's negative, one's positive. Neutron has 0 charge. At the same time, 10 to the power negative 19 is extremely, extremely small. So if you were to touch an electron, for example, it's not like you're going to shock yourself. It's so small. Okay. However, what do we say? We say that an electron has a negative 1 charge, a proton has a positive 1 charge, and a neutron has a 0 charge. What about our masses? Okay, once again, these are our actual masses. So if you had 1 electron, it's going to be 9.109 times 10 to the negative 28. That's a massively small number, extremely small number. So if you had 1 electron in your hand, you would not feel it. It's way too small, and it's in grams. Proton and neutron have the same mass. Okay, once again, it's still extremely small, but this is to 10 to the negative 24. So it's relatively much bigger than the electron. Okay, by 4 decimals, almost 1,000 times bigger. Okay, so what do we say that our masses are? Okay, so for an electron, we say it has a 0 mass. For a proton, it has a 1, and a neutron, it has a 1, right? When we're doing our protons, neutrons, and electrons and stuff like that, right? We typically keep protons and neutrons as 1s. Electrons have a massive 0, essentially, because they're so small. Now, it would take about almost 1,837 electrons to make up the mass of 1 proton or 1 neutron. That's what this number here is today. So that's why we only say it's 0. Okay? An electron does have a mass, but it's so small that we don't put into consideration. Okay, so once again, these are electrons, protons, and neutrons. Now, a couple other things what we should know. We should know our main groups. Okay, these are from our periodic table. Okay, so our main groups are, okay, I'm going to 1, 2, 13, 14, 15, 16, 17, 18. And that's what that's saying here. You should know by now, right? You should know your families. You should know your alkali metals, your alkaline earth metals, halogens, metalloids, noble gases, and so forth. Okay, so that's all that this is saying. You should know where your transition metals are, your alkali, halogens. Okay, lanthanoids and actinoids we don't use too much, but those are the two at the bottom here. Okay. Oh, sorry. Okay, you should know your alkaline earth metals, your noble gases, and so forth. Okay, some common things, metals. Okay, most of our metal, or most of our elements, over 80% are metals. Okay, metals are reflective. They conduct heat and electricity. They're malleable and ductile. Okay, these are definitions we looked at the beginning of the year. Non-metals are brittle. They're brightly colored. Some are gases at room temperature. Most are. Okay, and that's what that's saying here. And then you have your metalloids. Now, your metalloids are the ones that touch your staircase, essentially. Okay? Now, those ones kind of are in between metals and non-metals. So they have a little bit of characteristics of both. However, we say that they're poor conductors, they're shiny, and they're brittle. Okay? Shiny is a metal, brittle is a non-metal, so it's kind of a little bit of both. Now, most elements are solid at room temperature. Now, if you look at your periodic table, okay, mine isn't colored, but if you look at the one on our course website, it is colored. If it has black writing, it is a solid at room temperature. If it has red writing, which you'd see on your non-metal side, and hydrogen, those ones are gases at room temperature. And then blue, okay, there's only two, bromine and mercury. These are the only two liquids at room temperature. Okay, now we could take copper and melt it and turn it into a liquid. Yes, we can do that, but at room temperature, it's a solid. So that's why it has a solid there, right? You could take oxygen and freeze it into a liquid. It'd be extremely cold, okay? But at room temperature, it's a gas. So that's kind of where we have those here. Okay, and once again, that's why it says at room temperature, at room temperature, at room temperature. Next, you should know your diatomic molecules. Okay, there's 7 of them. Okay, so those 7 are here. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen. So it's 1, 2, 3, 4, 5, 6. And hydrogen there makes it 7. Each of those 7 at room temperature, okay, and naturally in the environment, they're typically paired up. So for example, hydrogen, you're not going to just find one hydrogen by itself. You're actually going to find 2 of them by itself if you saw it naturally in the environment. Oxygen, same thing. Fluorine, same thing, and so forth. All those 7 that I said before, all of them are going to have a little 2 there because they like to be grouped together. All right. Reactivity, we're going to look at that in a minute, so don't worry about this. Your Bohr model, okay, don't worry about that either. Okay, this one here, once again, don't worry about the stability of elements. We're going to be talking about that shortly. And then over here, there's a couple important facts. Okay, 92% of all the atoms in the universe are hydrogen. Okay, pretty much everything's made up of hydrogens. About 7% is helium, so that's 99%. Okay, only about 1% of everything else in the universe is other types of elements. Okay, now the reason why it's so high, these numbers, is because typically your suns and your stars are made up of hydrogen. Okay, and as you guys probably are aware, the suns and the stars of the solar system make up most of it. Okay, like if you think about our solar system, the sun is massive compared to all of the planets added up. Okay, so once again, that's why that's Those are facts over here. Okay, as an atomic number increases, the element becomes less abundant. Okay, and Earth's crust. So we have 47% oxygen, 28% silicon, 8% aluminum, 5% iron. I won't ask you that, but it's just interesting facts to know. All right. Now, this is for section 1.7 over here. And we're going to talk about periodic trends. Okay, now a lot of people have problems understanding this. Okay, so it is a little bit tricky to understand for the first time. So please pay attention while we go through this. Okay, if you need to pause the video throughout, just do so because it can get definitely tricky. All right. So the first one we're going to look at is something called atomic radius. Okay, now in order for me to better explain it, what I am going to do, I'm going to take a sheet of paper here, okay, to kind of draw it, and I'll keep it like this. All right, so the first one, atomic radius. Now, what is atomic radius? So if we go back to our Bohr-Rutherford diagram, okay, and we looked at this earlier this lesson. Okay, so once again, I'm just going to do a rough drawing of it. Here's my nucleus. I have my protons. I have my neutrons in here. And then I have my shells. Okay, I'm not picking any element in specific. I'm just drawing a random element per se. Now, from math, you guys should know that your radius is the distance from the center all the way to the furthermost circumference. Now, in an element or in a compound, for example, okay, our atomic radius is going to be the distance from the center of our nucleus to the outermost electron we have. This distance here, which we can measure in picometers, which is 10 to the negative 12 meters, extremely small, this is what we call our atomic radius. Okay, now, once again, it is an estimate as we can't really go into an atom and look that deep. The technology that we keep getting every single day as we progress through evolution as a human society. Our technology is getting better and better, so we'll be able to get exact measurements one day. However, how do we know which elements have a bigger atomic radius, which ones have a smaller atomic radius? So, there's two ways of determining this. The first way, if you had two elements, one was this one here, and let's say we had a second element, protons, neutrons. This one only had one shell. Which one's going to have the bigger atomic radius? Well, if I look here, this atomic radius is much smaller. It only has one shell, so those electrons are closer. So one way that for our periodic table, as we move down the periodic table, the more shells we have, the more energy shells. And the more energy shells we have, the bigger that atomic radius will be. And that's what we have here. Now, what if we had two elements? Okay, now we're going to do another example. What if we had, and hopefully you can see this, yeah. What if we had two elements? Okay, once again, I have my, maybe it might be easier to see if I do this. Okay. If I have my protons, neutrons. Okay. Let's say we have two shells. Okay, so our first example, we had two of them. Okay, maybe it might be hard to see. That's why I'm changing my marker here. This one had three shells. This one only had one shell. So the atomic radius is bigger. What if we had two that had the exact same amount of shells? Okay. Now, this one has one, two, let's say it has 1, 2, 3, 4, 1, 2, 3. And this one has 1, 2, 1, 2, 3, 4. Okay, so this one here would be fluorine, essentially, and this one here would have been carbon. Now, which one here would have the bigger atomic radius? Okay, now a lot of grade 11s can understand this here. Okay, the more shells, obviously, the bigger that radius is going to be. What if they had the same amount of shells? Well, what's going to happen is this. The more electrons you have means the more protons. Okay, once again, if you think about your protons, if you did your protons, neutrons, electrons, if you did it for both of them, you would notice that this one has more protons and more electrons. This one has less. So, because we have more protons and more electrons, think of them as magnets. The more magnets you have, the more of a pull you're going to get. So the more protons, the more electrons you have that are pulling the compound together, the smaller your radius is going to be. So for this one here and this one here, this radius would be smaller and this one would be bigger. Okay? So the more protons, the more electrons you have, the more, think of them as magnets, like I said. And the more magnets you have, it's going to pull everything closer and it's going to be more compact. And the more compact it is, the stronger that element is. The wider it is, it's not that stable. The more compact it is, the more stable it is. Okay? So that's why we have this here. Okay? So as we move down our periodic table, the radius is going to get bigger and bigger and bigger because the more shells. But if we move in this direction, going from left to right, well, we're going to add more protons, more electrons, right? Lithium only has 3, beryllium 4, 5, 6, 7, 8, 9. So the more protons and electrons we go going from left to right, the smaller that radius is going to be. And that's what we call a trend. And that's what we have right over here. So as we move down the periodic table, the atomic radius, because that's what we're looking at here, is going to increase. It's going to get bigger and bigger and bigger. As we move from left to right, the more protons and electrons we're adding, and then the smaller that atomic radius will be. So that's what we have for our first one. Okay, so that's atomic radius. That's our first one there. I'm going to skip down. Okay, hopefully, can you see this? Sorry, I'm going to try to move so you can see. Okay, next one we have, we're going to look at electronegativity. Okay. What is electronegativity? Electronegativity determines the relative strength an atom has. Okay. Now, electronegativity it goes hand in hand with atomic radius. Okay? And essentially it's this. The smaller the radius of the compound, the stronger it is. Okay? So, if we were looking at, once again, if we're looking at our examples here. Okay, here's my first one. Okay, this atomic radius was bigger. There was more shells. So this one is going to be weaker. Okay, this one's going to be weaker. Reason why it's weaker is because there's less of an attraction. It's a lot easier to just take an electron out of here because the electrons are so far from the nucleus, right? The electron and the proton are attracted to each other. So if it's really far apart, well, they're not going to be very strong holding on to each other. However, here, because there's such a small radius, the attraction between the proton and the electron is really strong. So we would say this one here is stronger. Okay, so the more compact something is, the stronger it's going to be. The more spread out it is, the weaker it's going to be. So same thing here. We have fluorine. Okay, so fluorine, because it has a small radius, okay, it's going to be stronger. Okay, even though it is smaller as a compound, it makes it stronger. Because this one's slightly bigger, it's going to make it weaker than fluorine anyways. Okay, so electronegativity is the strength an atom has, okay, to take an electron or to bond. So the bigger the radius, the weaker it is. The smaller the radius, the stronger it is. Now, another way you can tell is if you go to your periodic table and you go to the back side, okay, the one with all the values. Now, on the back side here, if you look at your key, over here we have something called electronegativity, and in bracket it says Paulings. Okay, Paulings is the name of the person who came up with it, of this idea of electronegativity, and he gave a value of all the compounds. So, once again, if you think about your trend, the bigger the radius, the weaker it is. So if you look over here at the bottom, francium, that's actually our weakest compound. It's 0.7. Okay, now take a look if you're going up. Next you have cesium. It's 0.79. Rubidium, 0.82. Potassium is about 0.82. Okay, sodium, 0. So it's getting stronger as we go up. Reason why? Less shells. What if we went from left to right? Okay, so francium is 0.7, radium 0.9, 1.1. So it's getting bigger going this way. Reason why? More protons, more electrons coming in together. So if you follow that trend, where should be our strongest one? Well, you would think it's be our noble gases, right? Because that's all the way on this side. However, our noble gases don't have any numbers there. Why don't they have any numbers? Because noble gases don't want to take any electrons. Okay? They're happy. They're strong as is. So that's why there's no value. However, the strongest electronegativity value would be fluorine. Okay, it's 3.98. It's the highest number. And the reason why it's the highest number is because it has one of the smallest radiuses, and it's only looking for one electron. So it's really, really strong. Okay, and if you take a look around it, it just keeps getting weaker. And once again, that's what we call a periodic trend. Okay, it's the trend around it. Now, if you take a look, you'll be able to see some exceptions. There are some exceptions. So for example, look at xenon. There's a number there, even though it's a noble gas. Okay, so there are exceptions, but the overall trend is this here. Okay, electronegativity gets stronger as you go from left to right, and it gets weaker as you go down. So it's the opposite from our atomic radius. Okay, so once again, our atomic radius is how big that atom is. The electronegativity is how strong it is to take an electron. Okay, so fluorine and our gases are going to be stronger because they're looking for electrons. Typically, our metals are losing electrons, so they're going to be weaker. So they're going to have a lower electronegativity. And once again, that's what it all says over here, as well as in our textbook. Okay, our last two, okay, ionization energy and electron affinity. All right, so in order to better understand this, we need to kind of remember our ionic compounds. Okay, so I'm going to just draw a little bit here, and then we'll talk about it. Okay, so let's say we had, and I'm going to do our Lewis structures. Actually, I'll do our Bohr-Rutherford. It might be a little bit easier to understand for a first time here. Okay, so I will draw sodium. Okay, so our first one is sodium. Now, I don't need protons and neutrons for this, so I'm going to leave it blank for this demonstration anyways. Okay, so sodium has 1, 2, and 3 shells. And then I'm going to work with, let's say, fluorine. Okay, fluorine Once again, I don't need protons and neutrons for this example, so I'm not going to worry about it. But I have my outer shell, or my inner and my outer shell. Okay, so for sodium, we have 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, and then we have 1 on the outer shell. And fluorine has 1, 2, and then it has 7 on the outer. Okay, you should be able to draw these by now. Now, what's going to happen is this. We have sodium and we have fluorine. We have a metal and we have a non-metal. So what's going to happen is this. Fluorine has a smaller radius. Sodium has a bigger radius. Okay, that's our atomic radius. Fluorine has a higher electronegativity. It is stronger. Sodium has a lower electronegativity. It is weaker. And once again, it has to do with that atomic radius. Now, because fluorine is stronger, it is going to go and it is going to take the electron from sodium. Okay, fluorine is going to go and take that electron from sodium there. Now, can fluorine just do that out of nowhere? No, it needs some energy. It needs energy to do that. And the energy that's needed to take an electron is what we call ionization energy. Okay, so for example, let's say we needed 100 joules or kilojoules. It doesn't matter what. Okay, I'll even put kilojoules here. Okay, joules is a form of energy. It's a unit of energy. So fluorine would need some energy to take sodium's electron. Okay, and that's what we call ionization energy. Okay, so the energy needed to take an electron is called ionization energy. And that's what we have over here. Okay, and I'll go back to this once we're done. Now, when fluorine takes that electron, and what I'm going to do is I'm going to just draw that electron here. Okay, so here's this X. Okay, that's where the electron's going. What's going to happen to the atomic radius of fluorine? Would the atomic radius get bigger or would it get smaller? Or would it stay the same? Think about this. Once again, it's adding another electron. It's adding another magnet. What happens to the radius when you add more magnets or more electrons or protons? Well, the radius is actually going to get a little bit smaller. Now, when the radius gets a little bit smaller, fluorine becomes more stable, right? It's becoming an ion. And once again, if you remember your isoelectronic, it's going to start to look like a noble gas. Now, the radius is going to get smaller because it's going to get more stable. When that happens, fluorine has a little bit of energy that it doesn't need anymore. So what it does is it lets off a little bit of energy. That energy that it lets off is what we call electron affinity. Now, this number is much smaller than the other. So this one might just be 2 kilojoules. Once again, I'm just making up numbers to give you an idea. Okay, so let's kind of talk about this again. Fluorine wants that electron from sodium, so it's going to take it. The energy needed to take that electron is what we call ionization energy. When fluorine takes that electron, now it has more electrons, so what it's going to do, it's going to start to become more stable, and it's going to start to come in on into each other, and that radius will become smaller. When that radius becomes smaller and that fluorine atom becomes more stable, it's going to let out a little bit of extra energy that it doesn't need anymore. Because something that is more stable isn't moving very fast anymore. It's slowing down. So because it's slowing down, it doesn't need as much energy, so it lets go of a little bit. And that's what we have here. Okay, so that is ionization energy, and this one is electron affinity. Now, what if I had this? Okay, so I'm just going to, once again, I'm going to draw another example here. Okay, so this time I'm going to work with, let's say, beryllium. Okay, so beryllium, Be, it has 2 on the inside and it has 1, 2 on the outside. Okay, and we'll still deal with fluorine. Or actually, let's do oxygen. Okay, so oxygen, protons, neutrons. We have our inner shell, we have our outer shell. So oxygen has 1, 2 on the inside. It has 1, 2, 3, 4, 5, 6. Now, beryllium and oxygen here. Oxygen wants 2 electrons, not just 1. So what's going to happen is this. Okay, so this here is the outermost one for beryllium. Typically, we like to go in order, okay, because this is the last electron for beryllium, and this is the first spot that oxygen wants to fill up. So we would say that we would take it. Okay, now once again, oxygen needs some energy. So let's say we had 50 kilojoules to take this first electron here. As soon as oxygen takes that first electron, well, once again, oxygen's going to get slightly smaller. The radius is going to come down, and we're going to let out a little bit of energy. Let's say it was still 2 kilojoules. Now, what if oxygen wants to take that second one? Is the energy needed to take that second electron? Do you think the energy needed is the same, more energy, or less energy to take that second one? Okay, so for the first electron, we needed 50 kilojoules to take that, that first electron. So to take the second electron, do you think we would need more energy, less energy, or the same amount? Well, we would need actually more energy. Okay, so it's easier to take the first one than it is to take the second one. So for example, it could be 70 kilojoules. Okay, now once again, same thing's going to happen. As soon as oxygen gets that second electron, it's going to get smaller. It's going to let out some electron affinity energy. Okay, but every single time we take another electron, it's going to get harder and harder. And that's what we have here. Okay, so let's go back and let's talk about this now. So ionization energy. That is when an atom gains or loses an electron. Okay. Now, the first ionization energy will remove the outermost electron. And then for multiple ionization energies over here. So as we keep taking more and more electrons, and that's what I was showing over here, the energy is going to increase. Okay? Now, as you'll notice, we have another trend. Okay? The elements that have a higher electronegativity will also have a higher ionization energy. Okay? These 3 trends are all the same. This one's opposite. Okay, and then we have electron affinity over here. Electrons can be added. So electron affinity is the energy that's released when an electron is added. And typically this happens in a gaseous state. Okay, now as you'll see, there are many exceptions to this pattern. But for the most part, that's what we have here. Okay, so where I could ask you a question would be something like this. Okay, let's say I asked for calcium and magnesium. I said, which one out of these two would have the greater atomic radius? Well, calcium has more energy levels, so calcium would have the greater atomic radius. Or I could ask, what about nickel and copper? Which one out of these two would have the greater electron affinity? Well, once again, so if you look at electron affinity, it increases going from left to right. So because copper is more on the right side, copper would have a higher electron affinity. And I could ask you that for any single element on this, right? I could ask you oxygen and phosphorus. Which one has the higher electronegativity? Well, oxygen would, right? And so forth, okay? And on our last page, of our lesson, that's what this here is showing. It's just all your trends. Okay, the one that I won't ask you, okay, I won't ask you about the reactivity of metal. So you can cross that one out. Okay, but realistically, all you need to remember, if you're trying to remember your trends, remember that atomic radius and electronegativity go in opposite directions. Okay, that's the easiest way. That's how I remember. Okay, I know how my atomic radius acts, and all I need to remember is that electronegativity goes in the opposite direction. And I also remember that electron affinity and ionization energy, anything that has an E in it, essentially, goes in the same direction. Atomic radius is the only one that's going in the opposite. Okay, so those are our periodic trends that we will be looking at this year. So please make sure you go through the textbook and read through it a little bit further, as there'll be a lot more examples in there as well. Okay, so thank you for watching and have a great day.